So the subject of my talk is going to be achieving the noise targets in natural ventilated schools with thermo-activated building systems. So I start with the description of the contents of the talk. So first, tabs on natural ventilation principles, acoustic attenuated ventilators, a couple of case studies, and then trying to quantify the advantages and disadvantages of different solutions, and then a summary with the conclusions. So tabs is an example of passive or low carbon cooling, so in the sense that it aims to have a low consumption of energy. The cooling is usually provided by the soffit because it's usually the surface that is available, and the cooling occurs by both radiation and convection. To provide cooling, the soffit slab needs to be at a temperature which is lower than the room temperature. And so this implies that if we are transferring heat to the slab, that after a while we need to remove it, otherwise it saturates and it will not be able to provide the cooling anymore. So removing the heat can be done basically by on two ways. Is either we have water pipes running inside the slab, and so the water circulates, carries the heat from the slab away. This is one possibility. The other possibility is to have nighttime ventilation. So basically during the night when the air is cooler, the windows are open and the nighttime air cools the slab. So I have here one job that we have been involved, the Hive library, and it's an example of water-cooled concrete slab, but it serves to illustrate the general principles. So we have so here is exposed concrete. The air enters through the windows, is cooled by the by the slab that is at called the temperature. It mixes with the rest of the environment in the room, gets warm, and then it goes up through the roof. So you can see here in this picture that there are these top hats where the air basically is extracted from the building. The water in the picture, the middle picture in the lower row, that is used for the cooling is taken from that river. Okay, so tabs is part of a passive environmental strategy. It's likely to be used in conjunction with natural ventilation and good day lighting. So you can see here an example of a air and light shaft for ground floor classrooms, and you have this pattern of airflow that I have just described. So the air goes in, and it is cooled by the concrete slab, gets warm, and then rises and goes out. So more particularly in the natural ventilation, it's used during nighttime because it's the time where the air is cooler and where the heat can be rejected. So why use natural ventilation? So it uses no fan energy, it uses no fan noise, and therefore there's a low airflow noise because the air velocity is quite low. It's low maintenance, uses no plant space, and there's a potential lower capital and running costs. And possibly most importantly is that people feel more connected to outside world and perceive that they have a better control over their environment if it is a natural ventilated building. So the natural ventilation, what are the issues? It relies on low driving pressures from window buoyancy, and it's a huge difference in between the pressures available for natural ventilation, 1 to 5 pascals, as compared to 100 to 500 pascals. in a mechanical system. And it requires large openings in the facade, but because of these large openings, it can be problematic in noisy environments. So these two figures here illustrate the pressure generated by wind as the driving force for ventilation, or buoyancy effect due to different densities of the air. Maybe I'll come back later to this. So acoustically attenuated vents. We can have a window, and then we are fine with the ventilation, but then it will be too noisy. Or then the second option is to have an acoustic vent, which will reduce the noise, but then we may not have sufficient air. And or we can enlarge the area of the attenuated vent, but then it may well occupy too much area of the facade. So we need to kind of find an optimum point between the required acoustic performance, ventilation performance, and the physical size of our attenuation, acoustic attenuation unit. So to provide the acoustic attenuation, we have basically three types of attenuators. It's either the louvers, where there is absorption in each of these blades, the splitters, where the flow runs parallel to the acoustic absorbent slabs, and then there is the circuitous path where the absorption is, for example, lining the band. And they provide different acoustic absorption performances. So what do we need from an attenuated vent in practical terms? We require that the attenuated vent is weatherproof, that it provides acoustic attenuation, and that is thermal insulated, and so there's a closing mechanism that allows it to provide thermal insulation. And I'm providing some examples of how we have done these. For example, in Brentwood School, there is a weather louver that it is shown here, where this is the air intake, and then inside the classroom is a perforated panel, and there is a lined 90 degrees bend, and so here's how it looks from outside. In Locking Castle School, we have so these are the inlets here, these grids, and so there is a 300 mil acoustic louver inside these units, and there is also a 90-degree bend, and so this performs slightly better than the previous solution because of the line, and has a manually operated insulated door to provide thermal but also acoustic insulation. And so here's how the door looks from inside. Another recently completed school, Cardinal School. The solution here was to have splitter attenuators, where you can see here is a bulkhead that has splitter attenuators, and there are actuators that actuate the external windows to control the amount of air coming in. And in this case, they are 1,200 long and 60% free area. Further example is the Hackney City Academy. It's an example of a school where there's a double skin facade, although the examples that I'm going to show you are for these units here on the top. So it's similar to the Cardinal solution, a bulkhead where the air comes in, is attenuated, and then there are these doors that are that control the inlet of air. A further example is Complementary University, and this achieves the highest performance. Is a circuitous path, so the air enters here through an opening window, and it goes down through this, enters the room through this perforated panel, and then it warms, goes up, and goes out again. This faces a rather noisy street, and it works pretty well. It's even the low frequencies, so the kind of diesel engine type of noise, is barely audible. There's quite a lot of buzz and taxis and so on, and so it's quite a good good solution. So how do these different solutions compare? So we have, again, we need a ventilation performance, we need acoustic performance, and we need the physical size, either minimize it or define the shape of the attenuator in a way that is sympathetic with the architecture. So what I'm going to provide in the next slide is data that compares the performance of the different ventilators at a reference level of 1 cubic meter and 1 Pascal pressure difference. And then I evaluate the acoustic performance and the physical size of the attenuator. So I fix the ventilation, and then I look at, for the different types of attenuators, what is the acoustic performance and the physical size of that attenuator. So what this shows here is, so we assume that as a standard open window would provide 13 dB attenuation difference to inside a classroom. So here this 53 means the level at which we don't need acoustic attenuation in the windows. This is an approximate, or let's say it depends on the area of the window and relative to the facade, and we. It's a generally accepted number, but it should be just accepted in a reference way. And so here on the vertical axis, then we have the external noise levels that the different attenuators could deal with as to achieve 40 dBA inside the classrooms. That is the standard noise levels. So it's BB93 plus 5 dB extension for the fact that we are naturally ventilating the space. So what we can see is that if we have, or starting from another point, 53, we probably don't get this in a city, but we may get it in a countryside or outside a big city. The case that where we don't need to have any attenuation, and as we go up in the noise scale, so if we have a lined band, we may be able to deal with the 63 external noise levels. If we introduce louvers, get a bit higher. Then if we need higher performance because of high external noise levels, we probably would go for splitters, as we have seen in those bulkheads. And then for even higher noise levels, we would get something probably more circuitous to achieve the higher performance. Although by reducing the free area of the splitters, we can also achieve higher performances, but then we need larger areas. So basically what this graph says is that as the noise level increases outside, and for a fixed amount of ventilation, and here is 1 cubic meter, that is more than the minimum required for, let's say, fresh air. It already takes into account some cooling in summer. There's some allowance for it. but it's as a reference case 1 cubic meter per second. What we can see is that as the noise level, external noise level increase, the volume of the attenuator also increases to achieve the same target internal noise level. So basically, in noisier parts, we need larger volumes to meet the large attenuated volumes to meet the standards internal noise levels. So the summary: acoustic louvers on 90-degree bands are good up approximately, and this should not be taken as a hard number, but it's this 63 that is 10 dB higher than an opening window, let's say, would deal with. The advantage that we don't need additional space for a weatherproof louver because it's integrated. Splitters are the most space efficient option for higher noise levels. They are aligned with airflow, and so they give the better ratio of acoustic attenuation to pressure loss. It is better to use a shorter splitter attenuator with a lower free area than a longer one with a higher free area. So this interesting conclusion in terms of design, in terms of minimizing the amount of space. And based on so this is based on space efficiency, but not true if the face area of the ventilator is more critical. Because if we have a lower free area, then we need a higher ventilator area for the same air to pass. So it depends what parameter is driving the design. And then the circuitous path solutions, as we have seen in Coventry, can achieve a good acoustic performance and have the advantage that they are relatively simple and inexpensive, but occupy significant volume. Thank you.